Hey there, it's Shannon Mathchick Myers, and today we're going to be looking at the first section of operational properties for the Laplace transform. So I apologize ahead of time. I am using the microphone that's on the iPad. I can't find any of my other microphones, so you may hear some tapping. Hope it doesn't bother you too much. Anyway, here we go. Section 7.3, Operational Properties 1. When you are done with your homework, you should be able to use operational properties of the Laplace transform to solve certain differential equations. In the next subsections, we'll be checking out several operational properties. Of the Laplace transform that provides us with a more extensive list of transforms. And then you'll see that list in Appendix C. I'll just put that in parentheses. (7.3.1) is translation on the s-axis. A translation. Evaluating transforms such as the Laplace transform of e to the 5t times t cubed and the Laplace transform of e to the negative 2t times cosine at 4t are straightforward if we know the Laplace transform for t cubed and the Laplace transform for cosine at 4t, which we do from previous sections. If we know the Laplace transform of some function f, so we have the Laplace transform of f at t is equal to some capital F at s, it is possible to compute the Laplace transform of an exponential multiple of f, such as the Laplace transform at e to some linear function of t, at, times f at t, by translating the transform capital F at s to capital F at s minus a. So theorem 7.3.1, the first translation theorem. If the Laplace transform of f at t is equal to capital F at s, and a is any real number, then the Laplace transform at e to the at times f at t is equal to capital F at s minus a. Pretty cool, huh? It looks very complicated, but comes out quite simple. So here's a little bit of a proof for this. If we start with what's given, the Laplace transform of e to the at, so given here, f at t, what we're going to look at is, by definition, we can find this by evaluating the integral from 0 to infinity of e to the negative st times e to the at times f at t dt. That's by definition. for a Laplace transform. Now, this in turn will equal to the integral from 0 to infinity. Now what I'm going to do is I'm going to just do a little bit of algebra on the exponential, right? So if I factor out a negative, I can write this as s minus a, that quantity, times t, just factoring out the t on the right side of s minus a and the negative on the left side. Sorry, there should be parentheses around f of t. And then we'll have times f at t dt. But what is this? This is equal to capital F at s minus a. Good so far? And if we just look at a little picture of this, just a quick sketch, you'd have something like this, where this is our f-axis, and over here we might have our s-axis. And if this here, let's say that this here was f at s, capital F at s, and we said that it looked like this. And suppose that we have this line down here, which brings us to the domain value of s equal to a, where a is greater than 0, then your transformed function would look the same in every way, but it would start here. So this one would be capital F at s minus a, and the pink was capital F at s. Cool, cool? Excellent. All right, so now it can be useful to use the symbolism, Laplace transform of e to the at times f at t is equal to the Laplace transform at f at t as s approaches s minus a. So you basically just plug in s minus a wherever you would have seen an s. So where s approaching s minus a means that in the Laplace transform, capital F at s of f at t, we replace the symbol s wherever it appears by s minus a. All right, the inverse form of 7.3.1. To compute the inverse, of capital F at s minus a, we need to recognize capital F at s find f at t by taking the inverse Laplace transform of capital F at s, and then multiply f at t by the exponential function e to the at. So the Laplace inverse of capital F at s minus a will be equal to the inverse Laplace at capital F at s as s approaches s minus a, And that in turn will be equal to e to the at times f at t, where f at t equals the inverse Laplace transform at capital F at s. So first example, find either capital F at s or f at t as indicated. So here we go. The first one, we have the Laplace transform of t times e to the negative 6t. So why don't we look at what we were just working with? This will be equal to the Laplace transform at t as s approaches s minus a, so that would be s minus our a is negative 6, because that's the coefficient of t. And then that in turn will be equal to the Laplace transform at t as s approaches s plus 6. Now, we know that the Laplace transform at t from previous work is equal to 1 over s squared. And we still have that business of s approaching s plus 6. And so we'll have that equal to 1 over s plus 6, the quantity squared. And we're done. Kind of cool little trick, huh? All right, instead of having to use that longer definition each time. So now, next up, we have the Laplace transform of e to the negative 2t times cosine of 4t. So we're going to use that same method. We'll take a look at the Laplace transform at cosine at 4t. So we're going to just ignore the exponential because we're going to adapt it by s approaching s minus a, which would be s minus negative 2. And again, that's from the coefficient to the t and the exponential. So we'll get our Laplace transform at cosine at 4t as s approaches s plus 2. Well, the Laplace transform of cosine of 4 times t is going to be s over s squared plus 4 squared. Again, we had derived that earlier. That is still going to, we're still going to have to change s to s plus 2. So we'll keep that notation in there. So then we will get, replacing s with s plus 2, we'll have s plus 2 over s plus 2 squared plus 16. And sorry, I'm going to move this up just a wee bit. So our next problem fits nicely. All right, now we have some inverse work going on. So we want to find the inverse transform. I'm going to switch colors here. Working our inverse of 5s over s minus 2, the quantity squared. So here, let's just kind of play with this a bit. We'll do some algebra so we can switch this around somewhat and go from there. So this is going to equal to the Laplace inverse of, we can bring the 5 out. right? And that's 5 times. Now, I'm looking at s minus 2, like that, that's probably our s minus a. So couldn't we rewrite s as s minus 2 plus 2? Do you agree that that is still s? Awesome. And then that would be over s minus 2 squared, the quantity squared. And then continuing, we'll have the inverse Laplace transform. We can bring the 5 to the front. And then we'll have s minus 2 over s minus 2, the quantity squared, plus 2 over s minus 2, the quantity squared. Just splitting it up. Now we can certainly factor out the 2 from the second fraction within that expression. So we'll have 5 times the inverse Laplace transform of, I can reduce this. I have 1 factor here for my s minus 2. So we'll just have 1 over s minus 2 plus 2 times 1 over s minus 2, the quantity squared. Now I'll split this into 2 transforms. Be careful with that 5 that's been factored out. We'll have 5 times the inverse Laplace transform of 1 over s minus 2 plus 10 times the inverse Laplace transform of 1 over s minus 2, the quantity squared. Just multiplied the 5 in with the 2 and then factored it out. Now, working backwards, this would be 5 times our inverse Laplace transform of 1 over s, right? And that is going to go as s approaches s minus 2. Good so far? And then plus 10 times the inverse Laplace transform of 1 over s squared. And then we're going to have s approach s minus 2. So we will have 5 times, we want to put in our exponential, a is 2. So we'll have 5 times e to the 2t. I'm going to write these in times 1 from that 1 over s. So the 2t represents the shift, and then the 1 over s is just going to be that transform of 1, or not the transform, the Laplace inverse of 1 over s is just 1. And then plus 10, we still have that first part is the same, e to the 2t, because we shift by 2. And then this one will just be times t, because that inverse Laplace transform of 1 over s squared is t. And then the shift is taken care of by e to the 2t. And so just simplifying, we have 5 e to the 2t plus 10t e to the 2t. And we're done. Cool? All right. Next up, we've got can't talk today, sorry. We have an initial value problem, and we want to use the Laplace transform to solve it. So y double prime minus 4y prime plus 4y equals t cubed times e to the 2t, y at 0 is 0, and y prime at 0 is 0. So here we go. Hold on. We have L or the Laplace transform at y double prime minus 4 times the Laplace transform of y prime plus 4 times the Laplace transform of y. We know that that's going to equal to the Laplace transform at t cubed times e to the 2t. We just applied the Laplace transform to both sides, and we know that the Laplace transform is a linear operator, so that's why it was able to go into each term on the left side. Cool so far? All right, so here we go. The very first part, all right, is going to be, so I'll do this one in purple. So this one will be s squared times y at s minus s times y at 0 minus y prime at 0. Good so far? And then the next one, we will have minus 4 times, I'll do this one in black, L at y prime, or the Laplace transform of y prime, will be s times y at s minus y at 0, and then plus 4 times the Laplace transform at y, which is just going to be y at s, and that's all equal to, from that t cubed, we're going to get 3 factorial over s to the 4th, and then that's s is going to approach s minus 2 because our a is 2. And again, we have that from here, the coefficient to the t in the exponential. Good so far? Okay, so simplifying the purple, we will have s squared times y at s. We know that y at 0 is 0, so that will be minus s times 0. Y prime at 0 is also 0, so minus another 0. And then minus 4 times, I'll just put them in brackets again, s times y at s minus y at 0, which we know is 0 from the initial conditions, and then plus 4 times y at s from the green, and that's all equal to 6 from the 3 factorial over s minus 2 because it shifted to the 4th. Cool so far? All right, so now just continue to simplify. We're just going to have on the left side, well, I'll just rewrite really fast so it's nicer. We have s squared times y at s minus 4 times s times y at s plus 4 times y at s is equal to 6 over s minus 2, the quantity, to the 4th. And then factoring a y at s off to the right side, we will have a plus 4, a minus 4s, and a and s squared. And that's all equal to 6 over s minus 2 to the fourth. And then we will have, do you all see that this right here on the left-hand side is s minus 2, that quantity squared, times y at s is equal to 6 over s minus 2, that quantity to the fourth. So isolating y at s, we'll have 6 over s minus 2 to the sixth power. All right, now working backwards here, or working with this portion, y at s is equal to, if I take a 6 out, and then I multiply by 1 over 5 factorial times 5 factorial, so it fits one of our formulas, over s minus 2 to the 6. It's the same way that we got this portion up here. Then what will happen is we will get y at s is equal to, let's see, we'll have, I'll reduce it in the next step. I don't feel like doing the math. 5 times 4 times 3 times 2. And then the 3 and the 2 divide out the 6 times 5 factorial over s minus 2. This is a 5. Sorry, my 5s look kind of like s's. And so we will have L at y is equal to 1/20th times 5 factorial over s minus 2 to the 6. And then what I want to do is apply the inverse Laplace transform to both sides. On the left-hand side, we'll just get y equals 1/20th times t to the 5th. And then to take care of that shift of 2, we have e to the 2t. And we're all done. And I think that's a pretty darn cool way to solve an initial value problem, don't you? Okay, so 7.3.2 is translation of the t-axis. So it's really cool. It's sort of like applying an on-off switch. So in engineering, we often deal with functions that are either on or they're off. These types of functions can be defined as using, or defined using the unit step function. So definition 7.3.1, unit step function. The unit step function, and the author does like a fancy U at t minus a, is defined to be, so U at t minus a is either off, so 0 would be off, from 0 less than or equal to t less than a, or it's on, so 1 would say that it's on, and that would be for t greater than or equal to a. So note, U at t minus a is defined on the non-negative t t-axis, since this is all we're interested in when studying the Laplace transform. So looking at this step function, you would have something like this, where this would be our u-axis, and we would have our t-axis. We can call this A right here, and we can say that 1 is over here. And then 0, the function 0 is just a horizontal line at 0. The function 1 is a horizontal line at 1. And so for the first portion, you would have this graph here, and you'd have an open circle at the A. And then right up here, you'd have the closed circle at the A, because it's inclusive. And this line here. So it's off from 0 to A, and it's on from A to T. So your function can be whatever, right? It doesn't have to be a horizontal line, but the unit function basically switches it on or off. So when a function f defined for t greater than or equal to 0 is multiplied by this unit function at t minus a, the unit step function, the unit step function basically, quote unquote, turns off a portion of the graph of that function. So in general, the graph of f at t times u at t minus a is 0 or off for 0 less than or equal to t less than a, and is the portion of the graph of f, which means on, for t greater than or equal to a. We can also use the unit step function to write piecewise defined functions in a nicer way, or in a more compact form. So if you have your f at t is equal to g at t for some 0 less than or equal to t less than a, and h at t for t greater than or equal to a, the way we would write this in using the unit step function would be f at t equals g at t minus g at t times our unit function at t minus a plus h, sorry I keep hitting the button there, plus h at t times our unit function at t minus a. So if you think of, a picture of that, you would have maybe, you could have something like this, where you have that portion of it, that t minus a portion of the graph turned off, right? So if this is a, right? And then you have whatever the graph is turned on after that. So suppose you've got some kind of, curve or something. Could have some curve, right, at a, going t greater than or equal to a, right? And that would be your f at t starting at, or your h at t starting at a. And then that g at t, maybe it's just at 0, right? It's just turned off until a. And again, this would be our u and our t. And then a function of the type f at t equals, maybe it's 0 between 0 less than or equal to t less than a. It could be, and so it's turned off there. It's turned on between a and b, not inclusive of b. And then it might be turned off again when t is greater than or equal to b. So this one here would be written as f at t equals g at t times that unit function at t minus a minus g at t times our unit function at t minus b. So this would be equivalent to f at t is equal to, I factor out g at t, and I get times quantity u at t minus a minus u at t minus b. So, I don't know, you could have something that if we have, for our f at t, we add those 2 zeros and then we add some g at t. So in general, you could have something like this. So now we have an A, we have a B, and we know that it levels out on either side. So the middle segment is where the graph is turned on. So you'd have this segment here is turned off, and this segment here is turned off, and then you'd have something going on in the middle. So you could have a line, you could have something else. Let's say it was linear. You could have something like that. That's your A. That's your B. Cool, cool? All right. So now let's take a look at the second translation theorem. So our second translation theorem goes like this. If capital F at S equals the Laplace transform at F at T, and A is greater than 0, then the Laplace transform at F at T minus A times that unit step function at T minus A happens to equal e to the negative A times S times capital F at S. So here's our proof. So the integral from 0 to infinity of e to the negative AS times F at T minus A times that unit step function at t minus a with respect to t is our Laplace transform of f at t minus a times the unit step function t minus a, and that in turn will equal to the integral from 0 to a of e to the negative st times f at t minus a times that unit step function at t minus a dt plus the integral from a to infinity of e to the negative st f at t minus a, and that unit vector, or not unit vector, sorry, unit step function at t minus a dt. So all I did is found some a, all right, that I can split, where I can split the integral, not just some a, since we're going t minus a, we're splitting it, because what's going to happen is this here is 0, right, for 0 less than or equal to t less than a, and over here this guy is 1 for t greater than or equal to a. So this will simplify quite a bit. We'll end up getting the integral of, or the integral going from a to infinity, because this first one zeroes out, and this portion is 1, so we'll just get e to the negative st times f at t minus a dt. And now if we let v, I'm not going to use u because we're already using a u, so we're going to let v equal to t minus a, and so dv will equal to dt. Okay, so now looking at this integral from a to infinity of e to the negative st times f at t minus a dt, that will equal to the integral from, well, if v is t minus a, let's do a little side work. V is t minus a, right? V at a would be a minus a, which is 0. So that would be my lower limit of integration. I'd still have infinity as my upper limit, so of course this is an improper integral, all right? And then looking at isolating t, t would end up being v minus a, v plus a, I'm sorry. And I think we have all we need. So we will get e to the negative s, in for t, we have v plus a, times f at v dv. Now we do a little trick here. We separate that exponential as e to the negative sv times e to the negative sa times f at v dv. So we can actually factor out the e to the negative sa times the, because it doesn't have a v in there or a t, integral from 0 to infinity of e to the negative sv f at v dv, which is just equal to e, I'll write it as negative as times capital F at s. And that, of course, is equal to e to the negative a times s times that Laplace transform at f at t. Pretty cool, huh? All right, so next up, we're going to be using this unit step function to find capital F at s or f at t, whatever we need to find. So we have this Laplace transform of e to the 2 minus t times the unit step function at t minus 2. So this is going to equal to the Laplace transform. I don't like the 2 minus t, so I'm going to factor out a negative. So this will be e to the negative t minus 2. And then that'll be good because we had a negative in our formula, the negative as. And then times the unit step function at t minus 2. Now, that's going to equal to e to the negative as, well, our a is going to be 2s times capital F at s, which will be equal to, so that will get us e to the negative 2s times 1 over s minus negative 1, which will be e to the negative 2s over s plus 1. And we're done. Good so far? Okay, so the next one, we've got the Laplace transform at 3t plus 1 times the unit step function at t minus 1. This one's a little bit tricky. I mean, notice that we want to get the g at t to look like the unit step function, what's inside that unit step function, right? So we might need to play around with this one a little. So here, this would be equal to 3 times the Laplace transform at t minus 1 times that unit function at t minus 1 plus, well, let's think about what we have here. 3 times t minus 1 is equal to 3t minus 3, correct? And so how have I adapted this? In order to get it back to true, I need to add 4, don't I? So to get this to be 3t plus 1, we need to add 4 to adapt. And then we need to follow through with our Laplace transform of our unit step function at t minus 1. Cool so far? So we're doing the same thing that we had done. We just need to break it up. Okay, and match the t minus 1 in the unit step function with our t minus 1 in the function. So here we go. This will be equal to 3 e to the negative s over s squared plus 4e to the negative s over s. We're all good with our result here. And let's check out our next problem. Sorry, on this one I made a typo. This should be e to the negative 2s. And so that will give us a equal to 2, right? And our capital F at s will equal to 1 over s squared times s minus 1. Good so far? So here we go. We are going to, before we start with the Laplace transform, we're going to have to do the partial fraction decomposition on this portion here, right? So our partial fraction decomp, 1 over s squared times s minus 1 is going to equal to a over s plus b over s squared plus c over s minus 1. So getting a common denominator, we don't have to write our denominator every time. 1 would equal to a times s minus 1 plus b times s minus 1 plus c times s squared. And so 0s squared plus 0s plus 1 is equal to as squared minus as plus bs minus b, I didn't do that on purpose, and then plus cs squared. So then 0s squared plus 0s plus 1 will be, we'll have a plus c times s squared, and then plus negative a plus b times s, and then plus negative b will be that'll be our constant. So that gives us a plus c is 0, because remember we match coefficients. And so we have 0 in front of that s squared. And then we have a negative a plus b, that'll be equal to 0 because that's the coefficient in front of s. And then we have negative b will be our constant. So a negative a plus b is 0, and then negative b is equal to 1. So from that last one, we know b is negative 1. So then negative 1 would have to equal to a for that to be true, right? Because we have negative a plus b is 0. And then we need a plus c to be 0. And so c has to equal to, if a is negative 1, c has to equal to 1. So at the end of the day, 1 over s squared times s minus 1 is equal to negative 1 over s minus 1 over s squared plus 1 over s minus 1. All right, so now let's get to work with this other stuff. All right, so I'll do this one in a different color. So we'll have, this will be equal to our inverse Laplace transform at negative 1 over s times e to the negative 2s minus 1 over s squared times e to the negative 2s. So I'm using the information from the partial fraction decomp and then multiplying it to the e to the negative 2s. And then plus 1 over s minus 1 times e to the negative 2s. So bringing that Laplace transform through and factoring out the negative from the first two, we'll have the inverse transform, Laplace transform of 1 over s times e to the negative 2s minus the inverse Laplace transform of 1 over s squared e to the negative 2s, and then plus the inverse Laplace transform of 1 over s minus 1 times e to the negative 2s. That will equal to negative 1 times, this will just be our unit step vector. I'm sorry, I keep saying vector. Our unit step function at t minus 2, and that's times our negative 1. The 2 is coming from the e to the negative 2s, and the negative 1 is coming from our 1 over s minus 1. And then we get minus t minus 2 times our unit step function at t minus 2. That gives us our second portion, the 1 over s squared. And then from the 1 over s minus 1, we will get plus e to the t minus 2 times our unit step function at t minus 2. And that's what we wanted. Groovy? I had a typo on the wrong problem on the last one. You can take a moment to write this problem down unless you're using a corrected version. If it looks like this already, you're good to go. So here, applying the Laplace transform to both sides, the y double prime will end up with, we'll just write it out. So we'll have L at y double prime plus 4 times L Laplace transform at y is equal to the Laplace transform at f at t, which can be 0 or 1. I'll figure that out later. So then we'll have s squared, capital Y at s, minus y at 0 minus y prime at 0 for the first portion, plus 4 times, we'll just get y at s minus y at 0 equals L at f at t. So then we will have s squared plus 4 times y at s, and then we have this extra minus a negative 1 from minus y prime at 0. The y at 0 is 0 from our initial values. And then that's equal to the Laplace transform at f at t. Let's take a look at L at f at t, the Laplace transform at f at t. So we've got basically this, unit time function, and it's got a shift of 1, and so our a would be 1. So we're going to have just a 1 over s, right? And then minus e to the negative s over s. That's going to end up being the transform for that f at t, L at f at t. So on this side, we will have s squared plus 4 times our y at s plus 1 is equal to that. Now we isolate y at s. That's equal to, I'm going to write it as 1 over s minus e to the negative s over s. That I'm subtracting 1, but I'm going to write it as minus s over s, and that's all over s squared plus 4. And so now L at y is equal to, I'm going to put 1 minus s together. That's going to be over s times s squared plus 4. And then minus e to the negative s times 1 over s squared, s times s squared plus 4. And then we'll need to do a little bit of partial fraction decomposition, so fun. So the partial fraction decomp for 1 minus s over s times s squared plus 4 is going to equal to a over s plus bx plus c over s squared plus 4, because it's an irreducible quadratic. And so I'll write this as 0 s squared minus s plus 1 is equal to a times s squared plus 4 plus bx plus c times s, getting that common denominator and then omitting that denominator. So 0 s squared minus s plus 1 equals a s squared plus 4a plus, oh, I'm sorry, that should be bs plus c, my bad. We're using s's, not x's. All right. And then we'll have plus bs squared plus cs. So now we have an a plus b times s squared. We have c times s. And we have for a, which will be equal to the constant. So we get a plus b is 0. Again, that's from equating coefficients. We get that c is equal to -1. And then we'll get that 4a is equal to +1. So A will equal to 1/4. That means that B is going to have to equal to -1/4 to make A plus B 0. And so 1 minus S over S times S squared plus 4 is equal to A, which was 1/4, times 1 over S, and then the B, S plus C. What did we get for B? We got a -1/4, and then C we got 1. So that'll be plus -1/4 times S plus 1 times C over S squared plus 4. And so let's rewrite that as (1/4) times 1 over S I'm sorry, I plugged in for C. I did not. That's just going to be a 1. And then we will have minus 1/4 times S over S squared plus 4, and then plus 1 over S squared plus 4. And now finally, to make this work with our, transforms, our inverse transforms, these will be the same. And then over here, we're going to write plus 1/2 times 2 over S squared plus 4 to make that cosine result. And now to do the partial fraction decomp for just 1 over S times S squared plus 4, we're going to get a different A over S plus BS plus C over S squared plus 4. So that'll be 0S squared plus 0S plus 1 is equal to AS squared plus 4A, and then plus BS squared plus CS. 0S squared plus 0S plus 1 equals A plus B S squared plus CS plus 4A. I guess we didn't need to do the whole thing again. So this time the A plus B is still 0. C is also 0. And 4A is again 1, which makes A 1/4, C is 0, and B would be -1/4. And so 1 over S times S squared plus 4 is equal to 1/4 times S, times 1 over S minus 1/4 times S over S squared plus 4. Coming back and replacing those in, right, we will have L at Y is equal to, so replacing our 1 minus S with all this stuff we found in pink, right, we will have 1/4 times 1 over s minus 1/4 times s over s squared plus 4 plus 1/2 times 2 over s squared plus 4. And then from that we subtract e to the negative s times the 1 over the one we did in orange, that faster one. So that one's just going to be times 1/4 times 1 over s minus 1/4 times s over s squared plus 4. All right, quite a problem, huh? And now we do the inverse. So if we take our inverse Laplace on both sides, then we will have, it feels like we need a drum roll or something, right? Y is going to equal to 1/4 times 1 for that inverse of 1 over s, and then minus 1/4 times cosine at 2t for this portion. And my apologies, I just realized that c should be -1. I'll do it in a different color. This should be a -1. That would make this minus, and we'd have minus 1/2 times 2. So this would be a minus. And so we'll have minus 1/2 sine at 2t. This one gets a little bit tricky, so we'll be subtracting. The e to the negative s means that, so this -1 times s means that a is equal to 1, right? So we're going to have quantity 1/4 times 1 minus 1/4 times cosine at 2. Instead of t, we're going to put the t minus 1. All of that will be multiplied by our unit function at t minus 1. And then we are all done. That was a bear of a problem. All right. Well, I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. If you do like what I'm doing, please subscribe and hit that like button. Bye.